To see you all here. My name is Devdatt, and I'm a professor. I have two hats on. So one is that I'm professor in the Division of Data Science and AI at Chalmers. And so as the name indicates, I mean, our main focus there is on developing new data science and AI methods and applying them in different areas. We cover a very wide range of modern AI techniques and application areas. And I'm happy to talk to you about that if you want to, if you're interested in knowing more about that. But today's the hat I have on today is as chief scientist of and co-founder of the startup whose name is now Replify. It was something else a few weeks ago, but this is how things go with the startup world. They're fast. So Replify is the startup company that it's a spin-off from Chalmers. You'll hear more about it in the course of today's discussion. My engagement with it is as chief scientist. So I'm only engaged with it 20% of my time. The rest of it is at Chalmers, at least at the moment. These things can change in the near future, depending on how, or in the medium or long-term future, depending on how things go. So you will never know. So we keep our minds open to everything. So, should we get into the core? Or
yes, please. Yes, do it. I think that we are very excited about.
Okay, so let me see if I can share my screen. There we go. So today's session discussion is about synthetic data, what, how, and quality. And it's really interesting because synthetic data is something that we've been working with at Chalmers for close to 20 years. I mean, we were doing it long before the current interest. We were applying it in many different areas, transport, health, epidemiology, which of course is becoming very hot today as well. So it's sometimes very funny when you've been doing things for 20 years and nobody really was that interested in it. And now suddenly the interest spikes up. But then, as we say, great, if it's always better late than never. So from that research, all those early research efforts, we finally took it out into the commercial world. And so we founded a couple of years ago a startup company, which was called then Synthetic Data Solutions. Also had other names, which we won't go into. But now it's at a stage where we are going to get we are likely to get some interest from investors as well. So now we are called Replify, that stands for replicator. And it's a startup. It came out of a spin-off from Chalmers, and we were located and are still located in the CampX ecosystem of startups at Volvo. So Volvo has this ecosystem called StartX, and we are part of that. And Anton and others have been sitting there for a while. So this is us at the moment. We are four, including me. So that's Stefan, who is our CEO, is Anton, who will be joining me today in presenting, and he's our data scientist lead. And we have Matthias, who has recently joined us also as a software developer, and he's probably going to expand his expertise and role with us as well. So as I said, you'll hear more about us during the course of the presentation. So I won't say more about it right now. We'll say, things will appear in the presentation, and then you can, of course, you're welcome to ask more questions later as well. So the discussion today is synthetic data, what, why, and how, and quality. So what I'm going to start off by is just leading into a short discussion on what and why. As I said, we were doing this long ago, but suddenly the interest has spiked. So why is this interest spiked, and what is synthetic data? So of course, we all know, you're all data scientists, and we all know that in this business, especially with the advent of deep learning over the last several years or a decade, that data is now the oil that AI machine learning runs on. For all these, especially deep learning applications, you need a ton of data. We all know that, but we also know, and this was something that one of the earlier sessions or earlier events in this series of deep dives in data was done by my friend Daniel Longkilde from Anatel, who are in the business of doing, as their name suggests, they're in the business of getting data for machine learning applications. And he had a long session talking about what are all the problems with real data. So data is the new oil. You need a lot of it, but there are lots of problems and issues with it. So there's the question of quality of annotations, especially if you use something like Mechanical Turk. And then most importantly, perhaps, is that it's an extremely costly process, both to acquire data and to annotate it. And here's just a simple estimate that you find from many people, that it takes roughly 15 to 45 minutes to annotate a single piece of image data, for example. And there are, you can find on the net various estimates, but the bottom line is that it's an extremely difficult and costly process. And people like Tesla, for example, are known to invest a lot of their resources into just this process of acquiring and annotating data. And then there are other things. I mean, with real data, there is always privacy issues. And this is especially serious when you have, say, data from the healthcare domain, or other things like that. There are always privacy issues. Another very important thing that people in autonomous driving face is that it's very hard to get the edge cases of interest. So when you're doing acquiring data and annotating it for perception systems and autonomous systems, then actually the most interesting cases are the ones that never happen, or all happen extremely rarely. That is when you have an accident situation, or unexpected pedestrian crossing the street. I mean, these are things that you hope don't happen, but these are what you need in order to train the edge, the perception system. So it's extremely hard to get hold of those edge cases. So you have stories of we have partners here at SAFER who have exploited the cheap labor of our students to annotate data, but the students have to sit there for hours without seeing anything of interest, and only extremely rarely do you find something that's of interest for them to annotate. So there are all these issues with real data, which makes it extremely hard for people who want to use data in their applications. And just to drive home this point, it turns out this is quite surprising. I mean, these issues that I talked about are general issues that all companies would face if they try to acquire and annotate their data. But it turns out that actually this is also an issue with benchmark data sets that people have been using in their research projects and so on for many years, and that are they are the foundation of all research and many of the best papers in machine learning. So even things like so ImageNet, everybody knows that at least with image application and vision, this is the benchmark data set. Everybody swears by it, everybody uses this, and so on. And it turns out that even ImageNet has a lot of issues. And so these are two recent papers that came out from two groups at MIT that some of you might be interested in taking a look at. So they went back to all these very standard benchmark data sets like ImageNet and others like that. And it turns out that all of them have very serious issues with ground truth. So there are multiple valid labels, there are ambiguous classes. And so when you have these kinds of issues, both in the training and the validation set, then it throws everything you say about the performance of models and so on into question. It's not really clear if the accuracy that you report based on the data sets actually says anything about how it's actually going to work in other applications. So this is one of those papers. Then there's another independent paper by by another group at MIT, and so they looked at several other data sets which are also not just ImageNet but other data sets that are also very commonly used, and so these are also in other domains like natural language processing, 20 News, Amazon reviews. These are very standard benchmark data sets used in NLP studies, and they find too that errors in these are numerous and widespread. And they have an estimate that 3.4 errors. There's about 3.4% of errors across these data sets, and in ImageNet they found it goes up to 6% in the validation set. So it turns out that even benchmark data sets actually, very surprisingly, have lots of errors sprinkled throughout them. So this basically sets the stage for synthetic data. So we'll say a little more precisely and be, get very specific about what synthetic data is and so on in the next part. But just to start at the outset with a very broad sketch, it's synthetic data is data that is not in the real world, but is actually created in digital worlds. And it's annotated in the digital world. And we will see later that there are many different sources of this kind of data. In particular, they can come from simulations or from generative models. But the important thing is that even though this is synthetic and artificial, the important thing is that it is in some mathematical, statistical sense, a reflection of properties that you want in the real world data set. And so the interest for synthetic data has spiked because people have realized that all these problems of real data sets, you can get away from them if you're able to deliver good quality of synthetic data. And this is a quote from one of the CEOs of one of these companies who uses these synthetic data. So he says you can use them to get unlimited data in order to train visual models. And so instead of spending months to find images to train an AI system, you can use synthetic data instead to generate high quality images over a couple of days instead of months. So it really reduces both the time and other resources, cost and other resources in addressing the data problem of AI. Of course, the key point here is going to be whether it's good enough or good. Is it so the key point there is when you say it's mathematically and statistically reflective of the real world data, what does that mean, and does it deliver on that promise? And we'll say a little bit about that. We'll start a discussion about that in the last part of today's presentation. So just to repeat, benefits of synthetic data, well, it's cheap and plentiful. And I'll put here an example that is relevant for us because you can do it, for example, from game engines. It's completely accurate, unlike all these issues with real data set we talked about, even the benchmark data sets, because here the ground truth is known with perfect accuracy, since we have just generated them from our specifications. And then, you don't have any of those issues with privacy and other data usage restrictions. And another extremely important point is now we can create all the edge cases we want of interest. So the fact that in real data, you never encountered these edge cases, you can address very directly here. You can create those edge cases to your specification. And you can make them very robust to common statistical problems. So just to round up the discussion here and hand over to Anton. So this is a slide from Gartner. So in their projections, they think that the future of AI lies more and more towards synthetic data, and that they have some estimates that up to 60% of the data that will be used in the near future will be synthetic. And so we've just made a case for why that might be the way that companies and so on would want to go. There are obvious advantages. Given, if we can deliver on the promise of reflecting the real world and being useful in the real world, if that's the case, then the potential is very large and almost unlimited of what you can do with that in AI. And it applies to a wide range of industries, automotive and robotics, financial services, healthcare, manufacturing, security, social media, etc. And so maybe that's enough of a motivation, and now we can dive into how you can create synthetic data. So this is a good time to hand over. This is a good time to put up a breakout question that can start you thinking about it. So if some of you may already have done that, but if not, maybe you can use this to reflect and think about it from your point of view. So is this thing that we discussed, the time and resources challenge for gathering and annotating real data, is that a challenge in your company or domain? What kind of challenges do you face there? Is it more in acquiring the data, or is it in annotating the data, or is it both?
Yeah, everybody sees my screen, I hope.
Yep.
Yeah, good. So yeah, we're going to talk a bit about how to generate synthetic data. Based on the questions we got in our room, I think a lot of people are already ahead of these slides and are looking forward to the more how do we look at quality in synthetic data and how do we verify and the domain gaps and so on. But we're still going to go through a quick couple of issues when we come to generating synthetic data. So first off, methods for generating synthetic data. There are a lot of options, data augmentation and randomization. You can use generative adversarial methods, variational autoencoder, but we're going to talk more about simulations and game engines, because that's how we generate data right now. So we have more experience with it, but we also use stuff like GANs for closing the domain gap between synthetic data and real data. Sorry, it glitches a bit. So just a quick recap when it comes to tools and simulators. A lot of you probably know this, but there is a lot of different open source and semi-proprietary options when it comes to game engine simulators and tools that allows you to create synthetic data very cheaply. So for example, if you create your generation in a game engine like Unreal or Unity, you can use code to generate whatever you want, like Devdatt mentioned before, both edge cases, but also get the annotations and stuff for free. One perfect example of this is Carla, which is a completely open source build on top of Unreal that focuses on autonomous driving, where you get all the sensors like LiDARs and camera, and they also have like basic radar, but they're still working on improving that. And you get bounding boxes, semantic segmentation, and everything for free. But to do this, we of course need models. We can't really run a simulation without a world, without car models, without everything inside that world. So for that, we use Blender, which is open source and free, and we're going to get back to that a bit. But this creates a new issue. Let's say we have a simulator and we want to create synthetic data from it. The whole reason to do this was to get away from gathering data, labeling data, and so on. But now we need to feed something else into the system. We need to create 3D meshes, textures, and all the other data needed to create these 3D worlds and to get this sensor data out and ground truth out. And this is, of course, now the new cost, the new problem, and so on. So to cite a Swedish paper from Linköping University, although it provides relatively easy access to virtual worlds, the game engine's approach to synthetic data generation is limited in several ways. Consequently, these methods do not scale well when the ratio to final images to number of scenarios or game levels is low. Secondly, even though the 3D world in many cases may be large, it is hand modeled and of finite size. This not only means that it is time consuming and costly to build, but also that the coverage of classes and features is limited and the dataset bias is inevitable. There are some solutions to this, of course. The first, just talking about the ratio between images and worlds, well, we need a lot of scenarios or a lot of worlds. But the second is a more pressing issue, hand model of finite size, time consuming and costly to build. This in terms leads to both the cost and lack of variation. Well, we need procedural generation of large worlds. And procedural generations, for those that aren't familiar with the term, is anytime we create 3D worlds or 3D assets from rules instead of hand modeling them. These rules of most likely include a lot of randomness. If, for example, if we want to create a road, it could randomly create infinite amount of roads, but it could also be from map data, or you could give it some other input than random. Sorry, sometimes my screen doesn't switch. Yeah. So here is our solution architecture to this problem. In the middle, you see the simulator, which We try to be simulator agnostic, but mainly work with Carla that we mentioned before. On the right, you see real sim that we're going to talk about later. That is about closing the domain gap of synthetic and real data. But on the left, you see World Maker, where we create 3D worlds in a scalable and high variation way. So what WorldMaker does, it's take in sensor data, map data, and random parameters to create 3D worlds. And we create then paths and roads, terrain, static objects, and also the dynamic objects, but then exports it in a way that fits pretty much any 3D engine or game engine or simulator. And this helps us solve the problem of hand modeled and finite sized, because we can create huge amount of variation very cheaply since it's done procedurally and very fast. If we want to create a real world, we still need either map data or sensor data from that real world. But if we want to create completely random worlds that doesn't exist, we can do that from random parameters. This project started in a Vinnova FFI project back in 2019 that we actually did together with Volvo, both Volvo Technology and Volvo CE, Halmstad University, and our sister company Embeddle. And in this project, the focus was on challenging conditions. So as you can see here, some example of a open site that Volvo wanted synthetic data from, or similar sites that Volvo wanted data from, but they also wanted with snow and rain and fog and so on. So just to give you a quick view of, so this is a quick example of a completely procedurally generated road. And it might not look that varied yet. This was created a year ago when our WorldMaker technology was in its beginning. But what's really cool about it is that it's like 42 kilometers long, and it took less than a day to generate. So the problem with finite size and hand model is solvable. Sorry, I didn't want to change slide when I, yeah. And here is another example when we created 3D worlds from sensor data. For example, like when a partner has a site or something that they want recreated, so they can run, instead of recording it once, annotating it once, and getting one data set from it, they can record it, we turn it into a 3D world, and they can run thousands of simulations in it and get sensor data from that simulation. Yeah. Okay, I think I was a bit quicker than I thought, but we're at the breakout question for the third session now. What would be the advantages and disadvantages of synthetic data generated this way?
You left off. So okay, so now we are at the final part of our presentation today, which is somewhat, it's kind of the climax, because everybody has been talking about this already and anticipating a lot of this stuff already. So let's get into this discussion. So in these, so we're going to, so this is a issue that somebody brought up in the discussion. It came up here that when you talk about quality of the data set here, what do you mean? And so the first point is that it's not about photorealism. We don't want to, we're not that interested in photorealism here. In the kind of applications we are talking about, at least these use cases with autonomous driving or similar with, these are the ones that we have been tackling most. I mean, but photorealism is something, of course, which is very relevant if this was to generate synthetic data for Hollywood movies and so on. That might be more of an issue there with photorealism. Perhaps the photorealism is more relevant in medical application. I don't know. I mean, those are use cases that we have not actually directed ourselves to at the moment. But in the applications that we are talking about, which is so far more about, we focus more on autonomous driving, autonomous vehicles in, not necessarily on highways, but it could be in pits, or it could be in other special types of driving scenarios. Photorealism is not that crucial there. And that was already in the discussion. I mean, there, the kind of questions you're more interested in is, what is the drivable surface versus what is not a drivable surface, and so on. And I mean, the bottom line is that when you're talking about AI applications, the question is not photorealism, but how good it is to train on the downstream AI tasks. And that will be to some extent domain and task specific and so on. So those are the questions that are relevant about the quality of the data set, and then the kind of questions that are really important and interesting, and this is, again, people have brought this up in the discussion, is that then the questions are more about diversity, completeness, appearance, object occurrence distribution. Those are the things that are relevant when you're talking about the quality of the data. And then, many of these studies, that some of the studies we're talking about and so on, that they have studied this with reference to some benchmark data sets, which, so there are some real world benchmark data sets, the Berkeley deep dive, cityscapes, new scenes, and then there are synthetic data sets, like scenescapes, cityscapes, and so on. And the question would be, in these data sets and these discussions, how do they measure up in these terms, and in terms of what is the difference it makes to the training and validation of AI systems. So here is, so we're going to flash a few results. I mean, of course, this is not very definitive, and so it's not the final story, but just to take an example of such a study which was conducted using these data sets that I just mentioned in this paper from a workshop on AI for autonomous driving. So the bottom line here is that what works well at the moment is to use a combination of synthetic and real data. So they show many examples here where you take a combination of synthetic and real data sets, and you can use them in two ways. You can either mix them up during the training, and you train your system with a mix of synthetic and real data, or you can train the system with synthetic data, and then you can fine tune it at the end with real data. And this brings back to another comment and question that came up in the discussion, that you might have a very small data set with very high quality. So you might have a real data set, but with very good quality real data set, but a very small one. And then this is the case where this hybrid approach brings you the most bang for the buck. So what you do is then you train the system, you do most of the training with synthetic data, and then you do a final fine training with this small high quality data set. And this gives, in fact, the best results. So the best results, as reported in this paper, is that fine tuning the synthetic, the model trained with synthetic data with some amount of very high quality limited data, that gives you, in fact, the best quality, the best results. And again, this claim is again verified in this study, that photorealism is not important here. It's the diversity of the data that makes most of the difference. And another thing that they found in this study is that when they train the model, it helps to combine many different synthetic data sets. So instead of training with just one synthetic data set, you combine different synthetic data set that adds to the diversity, and that improves the quality of the final model. So it's this combination of using the synthetic data in the initial training of the model, and then doing fine training with a very small amount of high quality real data. That at the moment is the best way to do things at the moment. Now, I mean, of course, in the future, if you improve synthetic data, that might change as we go along, but that will be a topic for future discussion when we improve the quality of synthetic data in many ways. And so one of the things that people have brought up here is that you want to close the domain gap. So there is a difference between synthetic and real data, and it would obviously help to close the domain gap without making it necessarily photorealistic, but closing the domain gap in terms of statistical properties of the synthetic and real data set. And this has to do with these questions that came up in the discussion, the texture, the variation in the texture, and so on and so forth. So all this variation that you have in the data that should match statistically properties you find in real data sets. And so how do we try to close this domain gap? And again, we would like to do this in an automatic fashion. And so this, of course, brings us into another very major area in modern machine learning, which has a lot of interest focused on it for not just this application, but for many other reasons, which is the question of domain adaptation. And so this general question here, which is, this is several people in our department, they focus their research on this question, that you have, unlike classical supervised machine learning, where you assume that what you train your model on, the distribution you train your model on, is the same that you will test your model on. So you assume in classical statistical machine learning that there's always the implicit assumption that the training data distribution is the same as the test and the validation data distribution. But domain adaptation is the case when this is not the situation. And this is, of course, typically what is going to happen in the real world. So this is therefore an extremely important problem, where you have a source domain where you train your model, and you have the test domain, the target domain, where you will test your model. And in general, of course, you don't expect that classifier or model that is trained on one domain is going to perform well on another domain. You could have poor performance in other domains. So domain adaptation is the area of machine learning which is about tackling this question. So how do you close the domain gap between source and target domains? And in our case, for us, this question boils down to, or the source and target for us happens to be the synthetic versus real data. And obviously, any advances in techniques that we have from domain adaptation would be very relevant for this problem of closing the domain gap from synthetic to real data. So, as I said, this is a very major area in machine learning, and there is a whole host of different approaches to this problem, and several people in our department have different approaches to tackling domain adaptation. Some use methods from classical optimization theory, including things called optimal transport. Others use these GANs and stuff that people have mentioned. Still others use what is called pack-based method. So there's a vast area of methods here, and all of this is going to be something that is very interesting and highly relevant for us to draw upon as we keep improving this aspect. So I'm not going to, we don't have the time to do a full discussion here. If you're interested, then I can highly recommend that you attend some of our machine learning seminars at Chalmers, where we have had several people giving talks on domain adaptation. And so here I'm just going to limit myself to saying, again, to repeat, that there are different ways of doing it. And classical methods have used what are called classical shallow models. So here you extract features from your source set and target set, and you have two different distributions, the source and the target distributions, and then you try to align these distributions. So you try to find a mapping that takes you from one distribution to the other, and you use that mapping to close the domain gap. Now, of course, with deep learning, this stuff has changed a lot into, again, trying to do it end to end and so on. So here, typically, what you would do is, or one typical way of doing this is, you fine tune deep models. So then you train your model on the source data set, and then you do a fine tuning on the target domain. And this is one way to do domain adaptation when you use these end-to-end deep learning models. There are other ways of doing this as well. So this is a vast area. We don't know the final story, but we will tell you something that we did in this project that Anton mentioned before, and our version of that, which we call RealSim. So maybe I'll hand over to Anton to talk about that now. Anton, you're muted.
Sorry about that. But now everyone can hear me, I hope.
Yes.
Yeah, good. So, as we've spoken about now quite a couple of times, both during the discussions and breakout rooms and stuff, there is a big domain gap and issues between synthetic data and real data. So a couple of years ago, we started a project that was aimed to close this domain gap with the technology that we call RealSim. RealSim started as a Vinnova FFI project. It was running between 2017 and 2019, together with AB Volvo, Chalmers, and Ytronic and Astacero. But of course, when we started this project, we didn't want to reinvent the wheel. There were already some work being done in this, even though we were early when it came to using guns for like this image-to-image translation. But one of the first techniques we looked into was a technique called SimGun, which was published by researchers at Apple, where they wanted to create, well, eye pose estimation, or which angle you're looking at, but they wanted to use synthetic images and translate them to real images, and was a very, very simple generative adversarial model setup, where you just had one refiner and a discriminator and an unlabeled set of real images, and trying to turn these synthetic images into real images. But this was extremely limited, didn't work that well on bigger pictures or more complex environments. They got some decent results on just eyes, but they were very low resolution, very simple images. But then we looked at a technology called CycleGAN, and CycleGAN is a really cool gun where well, their contribution was mainly the fact that if you can translate it from domain A to B and then try to translate that back from B to A, you get a circle loss, or you can see how consistent it is in both translation, and therefore getting better consistency in translating both ways. Then we looked at UNIT, which used a lot of what CircleGAN had already created or published, but also added this shared latent space that you see in the middle, where if we encode, let's say domain A is a synthetic image and domain B is real images, where if we encode these, we want them to learn an encoding on the latent space that is identical. So a car is still a car. It just doesn't care at this stage if it's the synthetic car or the real car. And this enabled kind of this, using the same circle consistency, but at the shared latent space. Enable better consistency between images and making the network better at making sure that translation became the right thing, so to speak. But there were still a lot of problems to solve. One of the first problems we faced, I call the bias versus variation issue. And that is if you train one of these translators to translate from A to B, and it starts to get really good at it, you can at the same time bake in a very strong bias where every image is kind of too identical to the domain you're translating to, and too limited in the way that, yeah, they only have a certain number of cars. For example, every car tries to turn into that car when you're doing this translation. But this can be solved by introducing a bit of noise into the model. And I should have had an image on this slide, but we experimented with introducing noise at multiple different layers, both in the encoders, in the shared latent space, or in the generators, to get variation while still having really good translations. But this variation can come at a cost as well, because once you start introducing these variations, you run into a different problem, namely, will that new translated image still both will it map to the semantic segmentation map that you got from the simulator, or Will it have completely replaced item, like a light pole turns into a signal, a traffic signal, or stuff like that? So to solve this, we had to kind of force it to not translate too much either. But at the same time, we wanted high variation. This was a bit tricky, but one technique that we used, tried and actually worked quite well, was to use an edge detection algorithm and use that as a metric or as a loss function. Saying that if edges has moved too much, for example, then we probably changed too much and it won't map well to the semantic segmentation anymore, or it will change too much what it is on the image. Yeah. Another issue was, well, if in this variation versus accuracy issue, we also used this edge detection against the semantic maps to see is the edges in the image space still identical to the semantic map. And this works also quite well, but then comes the issue of kind of unsupervised versus semi-supervised. One of our goals was to get away from having to label the real data. We get semantic maps for free in the simulator, but we don't really want to create them at all in the recorded data or the log data. But this is kind of a trade-off that you have to live with, because you still need to record and annotate some data, both because validation sets, but also because fine-tuning with real data showed to work, make the synthetic data work really a lot better. So a lot of these are kind of trade-offs. That leads into kind of the affordable versus expensive trade-off. If you don't have enough label data, you both going to reach a lower validation result, and you might not have enough validation data if you haven't labeled data. But at the same time, if you're labeling all your recorded data, then you're going to get back to it being as expensive as just using log data and skipping the synthetic data altogether. But as I said, all of these are kind of trade-off problems that we've been working on, finding the best compromise and the best combination. But at the end, as Devdatt said, the really trying to achieve isn't so much making the data photorealistic. We've noticed during our RealSim project that variation is more important than realism. So if we bring back, I'll go back to one of the questions we got earlier, but what happens if you create a world where you use the same materials and textures everywhere? Well, this is actually one of the things that we can either completely solve or at least minimize in this RealSim step. Even though this image doesn't look a lot more photorealistic than this image. This the left one is directly from Carla and the right one has gone through RealSim. And even though it doesn't look like photorealistic or even that impressive to the human eye, it actually was part of a data set that performed a lot better when training on synthetic data and evaluating on real data. So to some results, during this experiment, the first benchmark that we set was training one model on 100% cityscapes data. And in this case, it's the blue. And training one model on 100% Carla data, in this case, is the red. And we evaluated both on the cityscapes evaluation sets with mean intersection over union. And as you can see, there is this is basically the domain gap, or so to speak. The model trained on synthetic data wouldn't evaluate well on real data, which is not at all surprising considering what we're talking about. And just to clarify, this was done with the Deep Labs model because that was kind of the state of the art back when we did this experiment. But the best results in that experiment was when we combined about 20% cityscapes data and 80% Carla data with real sim. And as you can see, we've not only closed the domain gap in most classes, we even surpassed cityscapes result in some classes. But as I said, we still believe we still came to the conclusion that we get the best results when we still use some real data for fine-tuning. But the fact that we're beating the result in some classes still prove that we wouldn't be able to do that if we just use 20% of the subset of the same data set that we trained the blue on. But of course, in some classes, we're still behind. Fence, for example, was one of those classes. Then we have to ask ourselves, why? Is it because we don't have enough fences in our simulator? Is it because our real sim technology isn't good enough at translating fences, or what is the issue? So this is how we work to solve, to get a deeper insight into what is wrong and what we need to improve to create perfect synthetic data. First, we create the world with WorldMaker. Then we run this in a simulation to create synthetic data. Then we apply real sim. We get that refined data. We train a perception system, and of course, both on the pure synthetic data, the real sim data, and also on log data. And then we evaluate it on log data. This way we can see both how the synthetic data and the refined synthetic data compares to real data in each class. What you see down here is 3 confusion matrices for logged, synthetic, and refined. And that gives us the answer: do we need more assets, more domain? Is the translation not good enough? Do we just need bigger data set? It helps us answer a lot of questions. And then we continue iterate on this. Improve WorldMaker. Do we need bigger variation in materials, bigger variation in assets, or just more worlds? Run more simulation. Do we need more synthetic data and so on? Or do we need to continue work on real sim? And as we do this iteration after iteration, we start seeing how our synthetic data is kind of catching up with the real data. Of course, this is time consuming and hard work as well. But when you have a company that specializes in it, it's kind of do it once, then apply it multiple times instead of having to do it every time like you do when you record and annotate real data. So I think that was pretty much it for us. This is a short slide about people in our company, and I just want to say, if any of you are considering whether it's EU or a Swedish funded research project in synthetic data, we'd love to be a part of it. Or if we can provide any help or initiate any discussions about how we could help you with synthetic data, feel free to reach out to us. But we have one last breakout question, and that is, how much saving do you think synthetic data could provide in your application? And by saving, we of course don't mean just money. Most of you guys are data scientists, so you probably more interested in saving in terms of your own time and your own productivity.